Now let us consider a step source for an RC circuit. Say we have the following, where we have a current source, a Thevenin resistance, and a capacitor all in a parallel configuration. To determine the behavior of the circuit, we first must apply KCL at our top node. In this equation, we have our current coming from our source entering the node, where we have current I, which is our voltage potential per our Thevenin resistance running down our resistor, as well as the current running through our capacitor, expressed as C times the time rate of change of our voltage. Now, if we divide by C, we have the time rate of change of our voltage plus our voltage per RC is equal to I, our current source, per our capacitance. We recognize this is the same form as an RL circuit, where our voltage as a function of time is equal to our current source times our Thevenin resistance, which can be equated to a voltage source, plus our initial voltage potential minus our source voltage, or our source current times resistance, times e to minus t per tau. Thus, we're going to have the same solution methodology for RC as we did RL circuits. Now let us consider example 2, where we have a voltage source that supplies a potential to a 3 ohm resistor. After the 3 ohm resistor, we have a 5 ohm resistor and a 460 millifarad capacitor in a parallel configuration. If our voltage is a function of time, we want to determine our voltage potential across the capacitor as a function of time. To do such, we can analyze our system for all time before t is equal to 0. For all time before t is equal to 0, our voltage output is 7 volts. After time t equals 0, our voltage output is minus 7 volts. The response of the capacitor, given as a function of time, is V of t, our voltage potential established across our capacitor, is equal to our source voltage, VOC, plus a quantity, VO, which is our initial voltage, plus VOC, quantity e to minus t per tau. For all time less than 0, since we have a constant voltage potential across our system, there is no current flowing through our capacitor, and our capacitor is behaving as an open circuit. Thus, we can say our initial voltage as a function of time is 4.375 volts. This voltage is merely the voltage drop across our 5 ohm resistor. Since our capacitor is an open circuit, that voltage potential is merely found via voltage division of series resistors. Now, when time is greater than 0 seconds, we can use the formulation for our voltage. And to do this, we're going to convert our left-hand side, i.e. our voltage source and our 3 ohm resistor, into a Norton equivalent. That is, we're going to transform our voltage source to a current source, and we're going to move our 3 ohm resistor down into a parallel configuration with our 5 ohm resistor. In doing such, our 3 and 5 ohm resistors are in a parallel configuration with an equivalent resistance of 1.875 ohms. Thus, we can solve for a time constant, which is RC. We have 1.875 ohms times 460 millifarads, which gives us a time constant of 0.8625 seconds. Thus, the voltage as a function of time is equal to our current source times our resistance, which is equivalent to our voltage, plus our initial voltage minus our current source times our resistance, which is merely our voltage source, times e to minus t per tau. Thus, we can say our voltage as a function of time is equal to minus 4.375 volts, plus our initial voltage, which was 4.375 volts, minus the negative of 4.375 volts, e to minus t per tau. Or our voltage as a function of time is equal to minus 4.375 volts, plus 8.75 e to minus 1.159 t. Now, when we have a non-constant source, all we have to do is modify our equation in terms of our forced response. That is, anytime we had a constant source, our forced response was a constant value. If our source is nonlinear, say an exponential, our forced response is going to take a form of an exponential. Thus, the reader is referred to table 8.71 on page 339 of the text for the simple modification of our forced response based upon a non-constant source.